All right, very good. So thanks for coming to lecture number 3. So far, we went through the list that we wrote down on the first lecture, and we didn't go very far. So of the possible explanations for the Higgs mass and the cosmological constant, well, we've seen huge tuning because there was nothing to say about it, meaning that they're just accidentally small because two quantities that have nothing to do with each other cancel. Then we've seen the case where they're not calculable, because again, there wasn't much to say about it either. Well, okay, we did kind of go into the details of the standard model calculation for mh squared, but in the end, it was a simple exercise. It was just a one-loop calculation with just some insight into terminology. And then most of last time, we talked about symmetry, essentially supersymmetry scale invariance. And we've seen, as an example of scale invariance, the case of composite Higgs. And well, I should say as a disclaimer that each one of these ideas in principle would warrant a whole lecture course by itself, but not a 10-hour course like this one, but even a 6-month course. So I'm of course condensating everything a lot to give you, to expose you to as many ideas as possible and get to the crazier stuff that is being developed more recently. But before getting there, so today I want to give you another example where scale invariance is doing the heavy lifting, which has been historically very important, and it still is, which is the case of warped extra dimensions. And then we will talk about lowering the fundamental scale of gravity, which you probably know under the name of large extra dimensions. And finally, well, it's an ambitious program for a single day, but we're also gonna try to start talking about the multiverse. So before getting into this other example of scale invariance, let me just make a correction to be on the record. So if you remember the first lectures, we were using dimensional analysis to estimate the Higgs mass and the cosmological constant, and they told you that you could write something like this, and then I was putting a 16 pi square at the denominator because Planck is above, and they make X as a mass, but I had inverted the dimensions in my head. Really, the way you should see this estimate is more like adding something with the dimension of a coupling here, a coupling squared. And you can think of it as being order 1, so as being still gravity. So we are kind of imagining that we got to energies where gravity is important. Of course, it doesn't necessarily have to be order 1. And as we said the first time, there are many caveats on this estimate, and we're going to see some of them today. Not all of them. Then the other more sophisticated caveats are going to come in the next couple of lectures. So we're going to talk about the truly crazy stuff like UV-IR mixing. Or cases where gravity doesn't have a scale or doesn't have a scale in the traditional sense. So there's nothing that enters as a matching or threshold correction in the Higgs mass. But for today, we're still in more sane territory. And so let me tell you this other example about scale invariance, which is in some precise sense in one-to-one correspondence with composite Higgs to the ADS-CFT correspondence, but we're not going to talk about that too much. I mean, we're going to use the fact that you can map these 5-dimensional theories into 4-dimensional theories to simplify our calculations. But mostly, I'm going to give you the most condensed possible version of the 5-dimensional picture. And so imagine that you live in a slice of ADS. So your world is, well, I'm terrible at drawing stuff, but your world is an interval. Okay, so you have some brain at one end of your interval at y equals 0, and some other brane at the other end in a place that we're going to call YIR. And these branes are four-dimensional. So your metric looks like this. Here, the four space-time coordinates are contracted with Minkowski, as usual. Of course, gravity is potentially dynamical, so you should also wonder about potential fluctuations of this metric. So in principle, the position of this brane that we're going to call the IR brane is a field. So it has some constant value plus some fluctuations. And similarly, the four-dimensional metric is not just some Minkowski, but you have to look dynamically for a potential for these fields and see what's their minimum to convince yourself that that this object is stable. There's also going to be some fluctuations in the cross directions, but these are massive. So one can show that in the theory that I'm going to consider, they can be integrated out from the low energy theory, where these other fluctuations instead have some components that are massless. So we're going to mostly focus on these other fluctuations. But before that, let me tell you a bit more about the picture. So as we said, we have this peak coordinate that lives on an interval. And then we're going to put the standard model on this IR brane. And so the first thing that we can ask is, what's the fundamental scale of gravity in this theory? Or actually, how does the four-dimensional scale of gravity looks like in terms of fundamental parameters? And well, this is a simple exercise. So in the five-dimensional theory, you're just going to have the usual Einstein-Hilbert action. And actually, sorry, let me call G bar the four-dimensional metric and G the five-dimensional metric. Then you're going to have some term like this in the Einstein-Hilbert action, so the usual coupling of curvature. And well, if you integrate over the compact dimension, this will contain some term that looks like this. So there are there is an e to the minus 2, 4 ky coming from the determinant of the metric in 5D. But then there is another factor with the opposite sign coming from the metric with upper indices that's contracting the derivatives in the Ricci scalar. So in the end, you get this factor, and you can see immediately that, well, there's going to be other terms, of course, coming from compactifying these four dimensions. But you can read immediately from this expression that this object here is the effective coupling of gravity in 4D. So this is a dimension of a scale squared, and it's going to effectively tell you how strong gravity is on the standard model brane. And if you do the integral, which is pretty simple, you're going to get this result. And well, I mean, I've always defined m Planck squared with a factor of 2, so let me do this to be consistent with the previous lectures. So really, say that this quantity is Planck squared over 2. And now we're going to make an assumption. So as I said, the position of the IR brane, which is essentially equivalent of to the size of the extra dimension, is a dynamical quantity. But for now, let me imagine that this k times YIR is much bigger than 1. Okay? You should immediately be worried because I'm assuming a hierarchy of scales. But let me run with this assumption for 5 more minutes and then I'll justify it. So if this is really the case, then the fundamental scale of gravity in 4D is just the 5D one divided by some parameter that essentially measures the curvature in 5D. So this is one equation that will be useful to keep in mind. And then at this point, we can ask something else. So what happens, for example, to the X mass if we do the same exercise? So we start from the standard model Lagrangian that is stuck on a brane, and we integrate over the compact extra dimension. So this term here is going to contain also the X potential. Then we just integrate using the delta function, and we get, as before, this factor coming from the determinant, this time evaluated at the position of the IR brane because of the delta function. And then we have an opposite one coming from the metric that contracts the two derivatives. And so from here, you see immediately that if you canonically normalize the kinetic term, let me do it in another order. The X mass that you see in 4 dimensions is much smaller than the Lagrangian parameter that you started with. So you can even imagine that the Lagrangian parameter that you started with was of order of the fundamental scale in 4 dimensions. Sorry, not the fundamental one, but the effective gravity scale in 4 dimensions. But what you're going to see on your brane is something that is strongly redshifted. And one way to think about this is that the space that we described is warped, so it has a big curvature, and gravity is mostly localized at y equals 0. So if you plug in these fluctuations into the metric and expand it and look for a potential and then solve the equations of motion for the gravity in this 5th dimension, you will see that its wave function is very peaked on this y equals 0 brane. And instead, the standard model is living here. So even if your naive estimate for the X mass is that it should be of order m Planck squared, the small overlap between the gravitational coupling and us makes it much smaller than you naively would think on this brane where we live. So this is one way to think about it, and later I will show you also another way, which is quite different. But well, so to make this story work, as we said, you need this big hierarchy. So you need this fact to be true, which is puzzling. I mean, again, from dimensional analysis, you would expect that this YIR is of the order of 1 over k, since you don't have anything else at your disposal. However, there is a way to make this hierarchy natural, and it's based on the symmetry I advertised at the beginning. So purely from scale invariance, there is a way to make this hierarchy easy to explain. And the simplest way to convince yourself is, again, if you plug in these fluctuations into the action, and then expand and look for a potential for this T of X, you will find that it doesn't have a potential, or it has a purely scale invariant one, depending whether you put a cosmological constant in the bulk or not. And the reason is that this space, so ADS space, has a lot of isometries, including scale invariance. The easiest way to see it is to change coordinates. So if you make this change of coordinates, the metric looks like this. And then if you scale all your variables, you see that it remains invariant. So you shouldn't be surprised that when you plug in the fluctuations of the metric into the action, you get a potential that doesn't really have a minimum, which is scale independent. And so, I mean, the symmetries of this space are doing even too much work for you, in the sense that they're not stabilizing the precise hierarchy that you need to explain the X mass, but they're just telling you that this YIR could be anything. So it could run to infinity in principle. And so the way to really stabilize the hierarchy, so make it big but not necessarily infinite or an arbitrary number, is to break the symmetry a little bit softly. And well, the simplest way that's been proposed to do so is called the Goldberger-Weiss mechanism, and essentially consists in adding a scalar in the bulk with a mass term. And this is the 5D picture that I'm going to write down. As I was alluding to at the beginning, there is a 4D equivalent. And this 4D equivalent, the mass of the scalar in the bulk, is just a relevant operator that is breaking scale invariance by a small amount. And we're going to see to some extent both pictures at work. So we've seen that potentially this idea can explain a big hierarchy. And now let's see how we really stabilize it. So how we find the value of YIR. So as I said, we could just add the scalar. Actually, there's no need even to give it gauge interactions just to understand the mechanism. So let me make it a normal derivative. I'm going to add a cosmological constant in the bulk for completeness. I'm not going to really run through the calculation giving you all the details, but this cosmological constant here gives some potential to this modulus that determines the size of the extra dimension. Eventually, you have to tune it against the tension of the two branes in such a way that the cosmological constant on our brane is small and the observed one, but we're not going to go through the details of this today. We're just going to focus on the X mass. So for the purpose of the X mass, this term that's in principle allowed by all the symmetries, all it's doing is that it's contributing some term to the potential of this modulus here. And I'm going to show you this in a second. So first, however, let's see what are the consequences of adding this scalar. So you can start from the action and derive its equations of motion. This is a damped harmonic oscillator. okay, with some z-dependent mass, but we know the solution.
Sorry, Raffaele.
Yes.
I don't understand. This phi is a kind of smearing of the X field and the delta constraint, or completely independent of the?
No, this is just another
scalar
that I'm
okay.
adding in the bulk. So the X and
there.
all the standard model fields are all stuck to one brane.
Yes.
While instead this guy, as you can see,
is mirrored over.
Yes, well, that's what we're doing. So we're solving for its profile on the fifth dimension. And this epsilon is precisely the parameter that breaks scale invariance. And essentially, it's the mass in units of the curvature of the space. So you see, I mean, you can do the exercise that we did multiple times before, and just do a dilation on the coordinates, and you will see that the mass breaks scale invariance in the same way as in 4D. Okay, the power, I mean, it breaks it in a slightly in a different way. The selection rules are different, but it still breaks it. And so it's not surprising that this parameter is the one that controls the breaking of scale invariance. And what you can do now is plug back into the action this solution for the scalar, and then also plug in this expansion for the size of the extra dimension. In reality, we're going to find more convenient to introduce a field chi, which is going to be 1 over the position of the higher brane into this other coordinates, z. And I'm going to just conventionally take the position of the UV brane to be fixed. Of course, I mean, this doesn't make any difference. I mean, the problem is translationally invariant to some extent. And so this guy is really telling you what's the size of the extra dimension. So don't be bothered by the fact that I'm looking only at the position of the higher brane. And so, yeah, what we want to do next is to put phi back in the action, and then put chi in the metric, and see if we generate a potential for chi, because the minimum of the potential for chi is going to tell us if this hierarchy is realized or not. And to do so, okay, we might want to fix the integration constants in the solution for the phi equation of motion. And we're going to do it without really specifying the dynamics. So I'm just going to say that on the higher brane, phi has some VEV, okay? There is some Lagrangian that I can specify on the brane for phi that fixes its VEV. And I'm going to define this V1 parameter as the VEV of phi normalized to its natural value. And similarly for the UV brane. And it's easy to write, of course, Lagrangians, but they could be similar to a Mexican knot potential like the one we saw for the Higgs that fix the VEV of phi to some value. And as we will see in a second, thanks to scale invariance, we're not going to need any special conditions on these values. So this V1 and V0 can be order 1, as you would expect from dimensional analysis. So the dynamics generating them, it's trivial in some sense. So you write the most general Lagrangian you can that doesn't have a minimum at 0, and you get values of V1 and V0 that are totally fine and generate this hierarchy that you want. But let's see it explicitly. So, of course, well, I'm not going to do the whole calculation, but it's easy to convince yourself that if you plug phi back to the action and then also this chi, what you're going to get is the following. Some constant term that maybe I could have also dropped. And you see that if you see immediately that if you send epsilon to 0, the potential for chi looks scale invariant. So there are only terms that go like chi to the 4th. You don't see it immediately because it requires some work, but if you send the cosmological constant to 0, also the chi to the 4th terms go to 0. This is not so important, but in case you want to reproduce the calculation as an exercise, keep that in mind. The really important point is that you can look analytically for the minimum of this potential. And you're going to find that at the minimum, chi has approximately this value at leading order in epsilon. And so you see from here that the parameter that controls the breaking of scale invariance allows you to generate a big hierarchy of scales. So even if V1 and V0 are within order 1 of each other, let's say V1 over V0 is 0.1, okay? And epsilon is, say, 1 over 20, so nothing dramatic. Already, you can generate a very big hierarchy. So chi over kappa can be of order of mw over m Planck. So this is, again, the power of broken symmetries at work. And this is exactly what we wanted, because if you remember, okay, the position, this web of chi is going to be the position of the higher brane, which is precisely what we wanted. So maybe I've inverted my, yeah, I think I might have a typo somewhere there. There should have been a plus. So this is really this. Okay, so you see immediately that it generated the big hierarchy that we wanted.
Sorry, I don't understand. The potential is computed how?
Yes. So the
No,
potential
just I mean, you chi has a dynamics.
yes. So you put the solution for phi back into the action.
Yes.
And then this is the 5D metric. So it's where was it? Yeah. So it's here, right? So this G here. So this G, this minus G, is minus the determinant of this guy, and the metric is defined from the Lyle element like this. So essentially now I'm gonna write yeah. So I'm gonna just put chi inside. Chi is coming from Z. So Z, you can write it as so Z on the higher brane is chi, okay, plus its value at the minimum. And so when you plug it back into the action and expand the determinant of the metric and also the inverse of the metric, you're gonna get this potential here for chi. And there's gonna be a term that comes from the cosmological constant times the determinant of the metric. And you can, I think, see it relatively easily that it's the chi to the 4th term, because so in the determinant of the metric, you're gonna have 5 factors of this, and then the square root. So you're gonna have a 1 over kappa z to the 5th coming from the determinant. So maybe I missed a piece. Yeah, so now I'm getting the wrong power, but this is the procedure. So
you have also the inverse.
Sorry?
You have also the inverse. the match.
Yes, they have the inverse, but in the derivative. So I was trying to see that from the constant you were getting the chi to the 4 piece. But okay, but details aside, essentially you're treating the fields in the metric as dynamical and plugging them back in the action and getting the potential in this way. Okay. All right. So yeah. So here, well, okay. So if you really wanna be, precise, here you have this integral from ZIR to ZUV, right? So that's how you get back chi, because you're integrating the metric from one side to the other. So you're gonna get some kappa piece from the UV side of the integration, and the dynamical parts that depend on chi from the IR side of the integration. Okay. These are all the steps. Yeah, so okay, this was just a rather standard review of what is known as warped extra dimensions, which were proposed by Randall and Sandrum at the end of the 90s. In practice, as we said, what's doing the job of protecting the hierarchy is against scale invariance. And there is a mapping between these models and the composite X models that I was telling you about the other time. And we've seen an hint of this mapping when we found the 4D potential of this chi. So this chi is telling you what's the position of the brain in 5D. In 4D, it's the dilaton. It's telling you how much scale invariance is broken. And you can see it, at least heuristically, from the fact that, as we were saying, when epsilon goes to 0, it has a scale invariant potential, and when the cosmological constant goes to 0, it has no potential. So it's the Goldstone boson of scale invariance. Yes. This model yeah, so yes, so so if you have enough energy, you can resolve this new dimension. So essentially, what you would be looking for, let me. I think the easiest is if I get to the other kind of extra dimensions that I wanted to tell you. But so the short answer to your question is do the exercise that we just did, but in full generality for all the dynamical fields. Okay. Since this extra dimension is compact, you can, if you want, expand the fields in Fourier modes of these extra dimensions. So you will find some discrete set of fields. And then do the integral over the extra dimension. Then in 4D, it will look like you have a tower of new states with masses at discrete intervals. So for example, you're going to have extra gravitons that are massive from doing the exercise that we just did for the dilaton, but for the other components of the metric. So for example, if you use the expansions that we said before, you're going to find that these objects, once you plug them back into the 5D action and do the integral over, well, this is also a 5D coordinate, and you do the integral over the 5D coordinate, these objects are propagating field with a mass that is of order k with some times some integer. And so you can look for the states, for example. So you can make them, when you get to the scale m, gravitational interactions between us and the states become observable. And to make this idea work, yeah, so the scale of this extra dimension, it's about a loop factor above the Higgs mass. So in the end, this set of theories has predictions that are similar to what we've seen the last time. So you predict new particles at a scale comparable to the Higgs mass that you can, in principle, make at colliders. Then there are all sorts of variations. So if you put also the standard model fields in the bulk, you're going to see partners of also of the standard model fields in the same way. So you're going to be able to write down the standard model fields as 5-dimensional fields, and when you do the integral over the compact dimension, you're going to have some zero modes that are the actual standard model fields, and some higher Fourier modes that get a bigger mass of order k that you can, in principle, produce.
Why do you call it compact if you can make ES dimension?
Well, I put it on an interval. That's why I call it compact.
Oh.
But I could have put it also on a circle. It wouldn't have changed much. Indeed, actually, there is an equivalent description when you change coordinates to a circle. So now we have exhausted our very condensed review of symmetry solutions. Now let me tell you about something more brutal. Okay, so we've said multiple times that in the standard model there is really no problem. And even if the Higgs mass was calculable in the standard model, there would still be no problem because from dimensional analysis, you would expect it to be something like this, which is perfectly of the right order of magnitude. And so really what's bothering us and forcing us to think about high energies is this M Planck, so it's the scale of gravity. So what if, well, as I said, M Planck it's a band, so we don't really know what's the mass scale associated to it. Maybe the relation between a mass and a band is that a mass is equal to a coupling times a band. So maybe this this quantity appears huge, but it's just the consequence of a small mass divided by an even smaller coupling. In which case, there would be no problem at all, because whenever you do an estimate of the Higgs mass, what appears on this other side is also a mass. So maybe this mass associated to gravity is not M Planck, but it's something different. And let me tell you what's by far the simplest way of making this happen. So the simplest way just requires writing down the Einstein-Hilbert action that we wrote down a few times already. Now we are back in 4 dimensions, so my G is just the usual 4-dimensional metric. I could add a cosmological constant if I wanted to, but it doesn't really matter too much for this discussion. Because all that we're gonna do is, and okay, I could also add some standard model Lagrangian that describes matter. And this one instead is going to matter. So let's say that I'm some regime where the energy is much, much smaller than M Planck, and also the curvature is much, much smaller than M Planck. Then nothing prevents me from expanding the metric around flat space with these fluctuations being small. I can do this and plug it back in the action. And if I do it schematically, I'm gonna get the following. So I'm gonna get, let me drop order 1 factor. So I dropped order 1 factors and I also dropped Lorentz indices. There are many possible contractions, but it doesn't really matter for what we're going to say next. And the only important point is that, okay, this object here is nonlinear in H and contains many different terms. There are also terms with H or H squared, which comes from the fact that we took the curvature to be small, but not necessarily 0. So the linear ones come from the fact that the curvature is not necessarily 0. They're not crucial, but we can write them down. This H times T is the coupling to matter, so it's the contraction by these fluctuations of the metric with the stress energy tensor that we defined as usual as the derivative of the action with respect to the metric. So this is the stress energy tensor. So what can we do with this simple schematic Lagrangian? So the zeroth order thing that we can do is ask, does this describe a well-behaved theory of these dynamical fields that describe the fluctuations of the metric that we can call gravitons? The answer is not really, because if you rescale the kinetic term to have it canonically normalized, you see immediately that you have a bunch of irrelevant interactions. And if you compute, for example, scattering of 2 gravitons at free level, you're going to get something that grows with the energy squared. And if you compute it at 1 loop, you're going to get something even worse. And now let me imagine that there is not only the standard model, but there are a lot of new particles. So in this T mu, there are n new particles. At 1 loop, these are all going to enter the calculation. So I'm going to have some enhancement of order n from a series of diagrams. The easiest way in which you can think about this n here is actually really if you think that this term is normalizing the kinetic term of the graviton. So you're always going to get some correction to the 2-point function from all these particles running in the loop. And this is going to go roughly like n times your kinetic term. And then when you do this rescaling to canonically normalize it, you're going to have a factor of square root of n for each n Planck coming in. And so if you do it this way, well, the scaling with n is a bit different. You get an n also at 3 level and another n at 1 loop. But then what we care about is the ratio. So if you take the ratio, this is the right scaling. And you're going to get that at some energy, the 1 loop contribution is becoming bigger than the 3 level one. And if you keep computing loops, you get more powers of n and e over n Planck. So effectively, this series of loops is signaling that something is happening in your theory at around 4 pi n Planck over square root of n. And so if you are brave enough to say the words, you can say, well, let me take n to be 10 to the 32. Well, this what does this mean? Well, this means that something is happening to gravity at a scale of order the weak scale. So let me call it MW. So this is the dumbest and most brutal possible way in which our initial dimensionalized estimate for the X mass could be wrong. Okay? Maybe the energy scale, so which is the same dimension of a mass associated with gravity, becoming different than what we know at low fields is the TV scale. It's not M-Planck. So you might think that this is all I wanted to tell you about lowering the scale of gravity, because this is pretty unsettling if you see the number. But actually, well, secretly, what I told you about, okay, the warp next dimension story that I told you a minute ago does it in a much cleverer way, but it's secretly doing the same thing. And let me tell you how. So, okay, this is really the most silly toy model you can think about, but you can also be more precise and say exactly what's happening at this scale. And one potential thing that could be happening is what we've seen before. So maybe at this scale, you see a new dimension. And the consequence of having a new dimension is precisely that gravity is modified at this scale. So imagine that you have some one or more new dimensions at a scale of order 1 over this energy scale. Then if you ask what happens to gravity, so the Newton force between two masses, you're going to have that at distances that are much smaller than this one, so when you can resolve this new dimension, then gravity looks like this. So let me imagine that I'm adding n new dimensions on top of the force that we know. And instead, when you go in our world, so you cannot resolve these dimensions, then you're going to have a dilution. So essentially what we're saying is that gravity appears weak in 4 dimensions because there is some big volume, at least big compared to the fundamental scale of gravity, that makes it look weak. Well, before I presented to you the story in a very different way, so from a perspective of symmetry, but the fundamental mechanism that's telling you that the weak scale is the weak scale is this, also in the case of warped extra dimensions. And there is a simple way to see it. So let's say that I add to my theory these new dimensions, and now they're flat. Okay. As per this estimate, so I can do exactly what I did before. So I can do I can write down my Einstein-Hilbert action in this new number of dimensions. And then I can ask, what does the Planck scale look like in 4D? And this is going to look like exactly what we were expecting from Newton's law. So we get the same thing that we were getting before, so that the fundamental scale of gravity times the integral over the size of these new dimensions is what counts in 4D to set the strength of gravity. And that's precisely our result that we got here heuristically from Newton's law. And well, before we were getting in 5D, in the worst case, exactly the same, where kappa was the typical size of this extra dimension, so the inverse. However, well, if you remember in the previous example, we were seeing that this factor was not necessarily the TV scale, so this volume was not necessarily very big. So I didn't tell you what K was, but it could have been very big, and you would still have had a big hierarchy of scales between the X mass that you see in 4D and the one that you see in 5D. So it appears like I'm lying to you, that it's not really the big volume that is doing the work in the case of vortex dimensions. However, it's just a matter of choosing your coordinates, because every covariant action is invariant under a Weil rescaling. So if you have, say, these are all your fields, and these are all your couplings, and by couplings, I mean all the coefficients of all your operators, so also the dimensionful ones. But this action is exactly identical to this other action, where I rescaled all the fields and couplings according to the selection rules of dilations. So for example, the metric with upper indices is going to go to W to the -2 metric with upper indices. So this is my collection of fields. My Higgs boson is going to go to W times itself, and so on. And now let me pick W to be, now I forgot what I wanted to call it, what sign I wanted to give you, but let me call it, no, okay, I didn't forget. Let me call it this. Okay. Well, then you're going to get that your X mass in 4D is the same as your X mass in 5D, but you're going to get that your Planck scale in 4D, so this one, is very suppressed compared to, sorry, I should have done the opposite. So that your Planck scale in 4D appears big because of this factor. Okay, so it's again a big volume that is actually telling you that the weak scale is the weak scale, because this time the natural value for the weak scale in 4D, so in 5D, is going to be this one, which, sorry, it's going to be the fundamental scale, which can be much smaller than M Planck because of this volume suppression. So I don't know if I kind of confused you by going back and forth with big and small, but the bottom line of this exercise is that you can think about these vortex dimensions either as redshift in the X mass from a big scale in the UV to a small scale in the IR, and that you're measuring here in the IR. But you can equally well, by doing this Weil rescaling of the action, think of this dimension as just being big and making gravity strong at a low scale. Okay, so this actually also better answers your question as how you see them, because this is telling you that you're gonna expect to see these effects not too far from the X mass. You see the extra dimension even in the warp case not so far from the X mass. When we were seeing the warping here, it was not so clear, but now it's completely clear. And let's see, what else did I wanted to tell you about this? Well, this was the core. Of the idea. The big difference, where there is a big difference between these warped extra dimensions that rely on scale invariance to protect the hierarchy and these flat extra dimensions. The big difference is that here I'm just saying that R is big, okay? But the natural value for R is 1 over m, so it's the largest scale that you have in these new extra dimensions. And in the case of the warped ones that I showed you before, you have this neat symmetry argument from scale invariance, why you can stabilize a big hierarchy of scales and take R much bigger than its natural value, purely from scale invariance. In this other story where I'm imagining that the metric of this extra dimension is flat, the only way in which you can get this result that you need to explain the weak scale is by tuning. Essentially, to tune cosmological constant in the bulk against some other contribution to the potential of the dilaton, so of the modulus of these extra dimensions. The very last thing I want to tell you about extra dimensions and in some sense lowering the scale of gravity is that you can also think about this big volume factor as a large n. And well, this analogy is mostly just for fun. But let me show you, and let me tell you why it's just for fun. Actually, maybe the most important point of this analogy is that it's a bad analogy, okay? Because in the case of world extra dimensions, we have scale invariance that keeps the hierarchy stable. In the case of n, we have the fact that n is a discrete number that keeps the hierarchy stable. So you're not going to renormalize how many particles you have in the theory. And in the case of large extra dimensions, when they're flat, you have nothing a priori that stabilizes the hierarchy. And so even if you can see them as a large n effect, they are tuned, and instead just adding a bunch of particles in principle doesn't require any tuning. But okay, let me show you very quickly why large n and these large extra dimensions are similar in some sense. And let me just take, for simplicity, one extra dimension. So my metric is going to look like this. Okay, we're almost at the hour. Okay, after this, so I'm going to do this quickly and then take a break. So, as we said, well, we're imagining that we have some other dimension which is compact. So the fifth dimension is compact. So I can always expand the fluctuations of the metric in terms of, let's say, Fourier modes along the extra dimension. Let me call y as before the coordinate in the extra dimension. Then, again, I can do as we did before and plug this back into the action. And integrate over y. And then let me now imagine that this new dimension is a circle, so the integral is easier to do. So this time y is defined mod 2 pi. And okay, I'm gonna get an action for these fluctuations of the metric. I'm gonna write it to you in gory detail, even if it's not so important. Just to convince you that we are not only writing down squiggles in these lectures, but we also are sure of what we say when we say that a field exists and it's propagating. So now you see more explicitly also what I was telling you before about this extra modes with a mass in the extra dimension. So what we got here, among other things, is a quadratic term in the action, which looks pretty complicated, but it's quadratic. So you have a kinetic term with derivatives and a mass for these excitations of the metric that we can call the Kaluza gravitons of the extra dimension. So if you fix a gauge and look at the equation of motion of this NH mu news, it's relatively simple. So you have these Fourier modes obey an equation of motion that looks like this. And so, as you can see, gravity is associated to a dimension full scale also in 5D. And so also in this case, when you get to the scale m, just like in our world when you get to a Planck, you expect something new to happen. And so this theory has to be interpreted as an effective theory that is valid at most up to m. So the largest mass of one of these excitations of the metric that makes sense to consider is roughly of order m squared. And so the maximum m that n that you are allowed to consider is going to be determined by this relation. And well, lo and behold, if you use that now, this is your m Planck square in 4D, again, as usual, from the same exercises that we did before, then you're going to get that your max n is going to be of order of m Planck over m squared. And so if you want to explain the weak scale, your big M is going to be at the weak scale. And so the number of Kaluza-Klein modes that you're going to see in this theory is these 10 to the 32 numbers that you found, well, we all found so unpleasant before. So this is just to say that even if the 10 to the 32 number looks ugly, one can in principle package it in a nicer way. Although in the end, if you look at the symmetries, this is not such a nicer way, because in this story, as I was saying, you have to explain why this R is big, and you have no symmetry argument unless you resort to scale invariance as we did at the beginning. Yeah, I think this is a good place to stop. Maybe I'm just gonna say one more thing, which is kind of more of a phenomenological curiosity, which is if you literally do as I did, so with one extra dimension, this doesn't work because then you can ask what is R that gives you the weak scale. So what is R such that if you fix the Planck scale in our universe, this M is the weak scale. Then you get that this R is this. Where now n is the number of dimensions in addition to 4. So if you put 1 here, you see that this R is big. So you're going to predict deviation from Newton's law on solar system scales. So you cannot, I mean, this exercise to show you that there are 10 to the 32 Kaluza-Klein modes is fun, but it's incompatible with the experiment. If you want this idea to work, even accepting some tuning, you need n at least 2. Now, actually, 2, I think it's borderline excluded. Maybe you need even 3. But we know gravity at small scales pretty badly because it's much weaker than intermolecular forces and other things that can constitute a background. We know very well that there are no equivalence principle violating forces because there you can design a zero background experiment by comparing two equal masses. But if you just ask what's the strength of gravity at a millimeter, you don't know it that well. And that's why this idea existed at all in the 2000s, let's say. Now our knowledge is considered better than back then, but not so much better that you can completely kill the idea just from gravity. Okay, so I think we're done with this, and we can stop here, and then the next hour I'm gonna start talking about the multiverse, and yeah. Again, we're going to talk about old stuff like Busso, Polchinski, and Brown-Teitelbaum to start. Well, actually, before doing the multiverse, I'm going to just wrap up all these ideas and telling you what's the problem of having new states at the weak scale with respect to experiment. And then we're going to make a small aside on the cosmological constant and then move to the multiverse. So this list is incomplete. There is a big appendix here. We'll see the next hour.
Questions? Questions? Are there questions from the virtual room?
Yeah.
gain from this approach if we're going to assume significant tuning anyway? Why don't we just assume tuning at the beginning and not deal with it? I mean, is it a less significant tuning?
Not really. I mean, I mean, you don't really gain anything. It's more just a different way of thinking about the problem. In some sense, historically, it was important because then people started to think about these extra dimensions and went to the scale invariant case where you have asymmetry, and then very often you can calculate things in 5D that you cannot calculate in the 4D almost conformal version of the theory. Let's say that this was good mostly as a change of perspective. I mean, some very often there are ideas which maybe don't necessarily work as they are, but lead the community of thinking about the problem in different ways. And we'll see also other examples, so especially for the CC of things that didn't work, but then led to ideas. All right, so we've seen, at least in principle, without too many details, well, we gave a few more for supersymmetry, that all these ideas based on symmetry, and even the ones based on lowering the scale of gravity, predict new physics not too far from the Higgs mass. The problem is that when, on the one hand, we probed this energy scale at left and the LHC, and we found no new particles. And in addition to that, we also probed much higher scales indirectly by essentially testing the approximate symmetries of the standard model. And again, we found nothing. So this is telling us two things. On the one hand, if really one of these is the explanation for the Higgs mass, we have a non-trivial symmetry structure that implements the constraints that I'm going to tell you in a second. On the other hand, probably it's not realized right at the scale where it should be to explain fully the Higgs mass, but maybe it's realized at a slightly higher scale. So if MH is here, then your new symmetry comes in at some scale MS, which is bigger than 4 pi mx. And so when you do the calculation of the Higgs mass in these theories, you're going to have multiple contributions at MS, and you would have to accept some amount of accidental cancellation between what are otherwise order 100s. And at the moment, direct search is essentially force us to tune between 10 and 5%. So very roughly, this is of order, let's say, a few percent. By just not having found anything close enough to the Higgs mass. However, as I was saying, this is not all, because then if you ask if you've been able to probe also much higher scales than this, the answer is yes. Potentially much, much higher. For example, let's say that I added to my theory these operators. These operators can induce proton decay, coefficients, let's say, with a rate of order proton mass to the 5th over this big mass scale to the 4th. And we measure the proton lifetime, for example, at Super Kamiokande and SNO. You can either measure, for example, some specific decay channel, like this one, or be more inclusive. You get to slightly different bounds, but they're both very strong. So in this case, we get a lifetime that should be bigger than something like 10 to the 34 years. And here you get something of order 10 to the 29. which translates to this m that should be bigger than about 3 times 10 to the 16 GeV in this case, and 3 to the 10 to the 15 GeV in the other case. So already you know that whatever you do at this scale cannot mess up proton decay. So it has to respect to some extent baryon number. But this is not all, okay? This is, you might consider this a mild request. But we tested very well, essentially, as I was saying, all the approximate symmetries of the standard model. And here I'm just going to give you a short and non-comprehensive list, but it gives you an idea of how many constraints you have to incorporate in an actual theory when you try to explain the X mass. For example, you have to forbid also this other operator that can lead to neutron oscillations. And let's say the typical time scale of neutron and neutron oscillations, which is comparable to the inverse mass, is given by this big mass to the fifth over m neutron to the sixth. And again, if we look at bounds from, now I forgot what experiment, if you look at bounds, at current bounds, you get that this lifetime should be bigger than roughly 10 to the 8 seconds, which means m bigger than 10 to the 6 dV. And I can keep going. I'll just give you another example. It's not very educational to do this list. So imagine that you have this other operator in your theory. Let me write it in the Dirac notation this time. So this can induce a radiative decay of a muon to an electron plus a photon. And also in this case, well, the bounds are pretty good. So the branching ratio for this decay is constrained to be smaller than 10 to the minus 13, roughly, well, 4 times 10 to the minus 13, which corresponds again to a mass scale of order 10 to the 6 GeV. And there are many other constraints, for example, from mixing of KK bar mesons. So as you remember from our first lecture or second lecture, these are, you can roughly think of these as bound states of two down quarks. And you're going to get, again, the higher dimensional operators that induce this mixing should live above 10 to the 8 GeV if they have an imaginary part. If not, the bound is slightly weaker, but you start to get the picture. So we have all sorts of approximate symmetries in the standard model. Here are flavored symmetry, so mixing between generations. Here are another type of flavored symmetry, mixing between leptonic generations. Here baryon number, in the case of proton decay, again baryon number, that are all apparently preserved up to very high scales. And so, other than just pure tuning, like cancellations between parameters that you need from direct searches, so by pushing the scale of the new physics somewhere above where you would expect it to be, you also have some extra, let's say, not tuning, but complication in model building, because you have to add all the structure that preserves these symmetries. I mean, to be fair, this was well known also before turning on the LEP and the LHC, and didn't stop us from believing that we would still find these symmetries. But now, as time goes by and we keep looking at this energy scale and we keep pushing the bounds on the masses of these new particles higher and higher, we're starting to lose faith, probably just for psychological reasons. But this is roughly the reason why now people are starting to consider more adventurous options. And what comes next is a review of these more adventurous options. And I will try to be neutral, and I will let you decide whether you prefer these ideas based on symmetry with some amount of tuning and some extra complication due to adding this approximate symmetries of the standard model, or if you prefer these other ideas that instead can, in principle, decouple completely the scale at which you see new states at collider, but requires some extra structure that is typically hidden at higher energies. Before that, though, let me just comment very briefly on the cosmological constant. So all we said about the Higgs mass holds also for the cosmological constant. In particular, you can use the selection rules of dilations to estimate it in the standard model. You're going to get something like this with an order 1 number. And again, you can get the 16 pi squared by restoring units to h slash and asking what dimension the CC has, which is a Vev squared times a mass squared. So if you put a mass to the 4th here, you need an extra h slash from the loop factor. So you can do this estimate, and you can already see a tension purely within the standard model, because on this side you have milli to the 4th, and on this other side you have about 100 GeV to the 4th. So just purely within the standard model, even without gravity, you have some tension of order 60 orders of magnitude. However, just as for the Higgs mass, if you do the actual calculation of, say, the cosmological constant that you measure, you're gonna have some. Let me imagine that I even forget about the top quark, but I want to do the effective theory calculation that we did in the first lecture at a scale where I'm integrating out the electron. Okay, so I'm matching a low energy theory with just neutrinos and photons to a high energy theory with electrons. Then you're gonna get some value of the cosmological constant at the matched scale, let me say at the electron mass, plus something like this. And then, well, there's going to be logs and other terms, just as we got for the Higgs. But the important point here is exactly as we had for the Higgs, we have something that we can calculate in the low energy theory, plus an object that essentially parameterizes our ignorance of high energies. So the calculation is not saturated in this low energy theory. And so all we can do is measure the cosmological constant to fix this unknown high energy contribution. And so we will never find a sharp problem purely within the standard model. We will never be able to write the observed cosmological constant just as a function of other things that we measured independently of it. So the situation is exactly the same as for the Higgs mass. It's just more dramatic because you have a big problem even if you completely forget about gravity. And for this very same reason, all these stories that we just told for the Higgs in terms of symmetry and lowering the scale of gravity do not apply to the cosmological constant. So there is no way in which we can explain this tiny number in any of these ways without accepting a 60 orders of magnitude accidental cancellation. Because if, let's say, supersymmetry was realized right there where you need it to explain the Higgs mass, then still you would have to explain why the cosmological constant is 60 orders of magnitude smaller. And in this case, you would have an actual problem. Because as for the Higgs mass, supersymmetry and also scale invariance make the cosmological constant calculable. So if really you were to UV complete the standard model in the MSSM or composite Higgs at the scale of the Higgs boson, then you would have a huge problem for the cosmological constant. And let me show you, at least in SUSY, why. So in SUSY, it's easy to see that the cosmological constant is calculable because, well, the Hamiltonian is just the zero component of the form momentum. And if we use the algebra that we wrote down the other day, you can rewrite this zero component of the form momentum in the following way. And so now if you ask what's the cosmological constant, so the value of the Hamiltonian, this is going to be the vacuum expectation value of the potential, so really the cosmological constant. And well, using this relation, you also see that this is equal to two supersymmetric generators acting on the vacuum. So the moment the cosmological constant is not zero, the generators of SUSY act non-trivially on the vacuum. And so cosmological constant equals zero is a special point for supersymmetry. And again, if we try to do this dimensional analysis estimate now in a theory with supersymmetry realized at some scale, we're going to get something like this. So that the largest scale that can enter the cosmological constant is the one that is breaking supersymmetry, and it cannot be anymore an arbitrary large scale. Similarly, for scale invariance. For scale invariance, it's even easier because the cosmological constant is just multiplying the identity operator in the action. So if you do a scale transformation, you're going to get that to restore scale invariance, your cosmological constant has to transform non-trivially. So it's a spurion that breaks this symmetry. And so again, if you do this estimate in a theory which respects scale invariance up to some scale, you're going to get that the biggest scale that can enter the estimate is the one that breaks scale invariance. And so in these theories that are either supersymmetric or scale invariant, the calculation for the cosmological constant is saturated at this scale. And so if experimentally you get there, you can actually now compute what was an unknown matching calculation in the standard model, and you can compute it in terms of observables that in principle you can measure independently of the cosmological constant itself. And so just like for the X mass, in these theories, you're going to get that the actual measured cosmological constant is a function of measured parameters, let me say SUSY breaking, and so on. And if the scale is much bigger than the observed cosmological constant, then you have to explain why these contributions that in principle have nothing to do with each other cancel exactly to give you the small result. So I went quickly because it's exactly the same for the X mass. One important difference with respect to the X mass that we're going to make use of soon is that the cosmological constant is the most relevant operator in the standard model Lagrangian. So you see it goes like s to the fourth. And so it has an even more dramatic impact on phenomenology of low energy than the X mass, which is the second most relevant operator in the standard model Lagrangian. And to see this, well, we have to turn on gravity. So imagine that we live in an isotropic and homogeneous universe, so approximately translationally and rotationally invariant universe, which is the case. Then I can write a metric for this universe like this. This is the most general metric that I can write, which is translationally and rotationally invariant in 4 dimensions, but as some non-trivial dynamics. So there is this parameter A of t that depends on time. And so as we did before in these extra dimensions, we can ask what's the dynamics of this parameter giving gravitational interactions. So in this universe, let me imagine that this is all there is. Which is actually the case for our universe today. So this is the dominant contribution to the dynamics of the metric. So I can take this action and derive the Einstein-Hilbert, sorry, the Einstein equations, so the usual G mu nu equals T mu nu times the gravitational coupling. And in this background, they're gonna look like this. So I'm defining this Hubble parameter as the time derivative of the scale factor divided by the scale factor itself. And in this universe where there is nothing but the cosmological constant, they look like this. Where now, well, I will never do it again, but since cosmologists use a different definition of the cosmological constant, I wanted to show you at least once. So this lambda here is really 8 pi g Newton times what I call the cosmological constant, or with the definitions that we used up until now, the cosmological constant divided by m Planck squared. So this is an object that has dimension 2 in energy. This is what I might often call Hubble when the universe is dominated by the cosmological constant. So it's a constant with dimensions of energy squared, which essentially already incorporates the gravitational coupling. So it's telling you what kind of impact a given energy density has on the expansion of the universe or on the dynamics of space-time. So now we've written down the equations that govern the dynamics of the universe, and we can solve them. They're very simple. You see, I mean, they are essentially an harmonic oscillator and an ordinary differential equation with a single derivative. And the solution, well, it's easy to get. It's just this. And one can show that when the cosmological constant is positive, the second term is going to be 0. Okay, not exact. I mean, it depends also on other parameters of the universe. But here we're looking at a simple universe with 0 curvature, just the cosmological constant. But in this case, one can show this. If you don't believe me, you can do it as an exercise. And so essentially, if the cosmological constant is positive, we have a universe which is expanding exponentially. This means that very rapidly you're going to be in causal contact with a very small neighbor of yourself. So everything around you is expanding exponentially. Information travels at the speed of light. So very soon I will not be able to give you this lecture any longer. And there is a simple way to see that in this metric. So you plug this solution back here, and then you ask what's the causal structure of space-time. Essentially, you ask how far a signal can travel at the speed of light from an observer, and what's the region in causal contact with it. The easiest way is to change coordinates in such a way that the coordinates don't look like they're expanding anymore. But the bottom line, okay, is that very soon you will see that the region that is in causal contact with you is of order of 1 over Hubble. So it's of order of m Planck over the square root of the particle physics cosmological constant. And so you see that if the cosmological constant is big, in particular maybe order m Planck as we expect from the naive estimate, you end up being in a very small universe. Okay, so this is roughly the maximal size of the observable universe when the cosmological constant is positive. When it's negative, the solution is the opposite. So now you are contracting exponentially. In reality, well, yes, it's not really that C1 is 0, but the solution is such that you're contracting exponentially until the universe has a size. So now the radius of curvature of your universe is again of order 1 over Hubble. And so again, you are in a very similar situation as before for the opposite reason. So now everything shrunk around you to the point that it's of this size again. And so this is the precise way in which, I mean, this is what I meant in the very first lecture when I said that the cosmological constant determines the maximal size of the observable universe. The reason, which we're also going to use in the following, which I'm going to state without proof for lack of time, is that let me now imagine that there is not only the cosmological constant, but also other forms of energy. Again, isotropy and homogeneity tell me that I can go in a frame where I can describe the energy momentum tensor of whatever matter I'm adding to my theory. I can describe it as a perfect fluid. So it's going to look like this, with some energy density in the 0,0 component and some pressure on the rest of the diagonal. In this case, I can write the equations in a relatively simple way, which is the following. In principle, I can also add curvature if I want to. Then, if I solve these equations, again, I can find some dynamical solution for A. But I can also then plug this solution back in and see how these energy densities and pressures scale with time. And what you're going to find, which, as I said, we're not going to be able to derive, but it's a simple exercise, is that, let's say that rho comes from a relativistic particle. So we're going to call it radiation. This scales like a to the minus 4. If rho comes from a non-relativistic particle, it scales like a to the minus 3. And A always grows with some positive power of time in both cases. So what I just told you, and please believe me, is that eventually the cosmological constant will dominate. So no matter what you put in your universe initially, its energy density will decrease as the universe expands. So if we plot the energy density as a function of time, you're going to have something, so the massless particle that go down pretty fast, the massive particle that go down a bit more slowly, and then the cosmological constant that stays the same. And so at some point, necessarily, it will dominate, and then something like this will happen, and the maximal size of the observable universe will be what it will be, depending on the value of the cosmological constant. And, well, this is an important fact that we're going to use in a second. Is it already almost time to? What time are we finishing exactly?
Finish when you are at a good point. I mean, no.
That's a dangerous thing to say. Okay.
Okay.
No, because it seemed I felt like when this last hour went too fast. Right? It's because we started at 10 past or something, right? But anyway, let me continue until a reasonable time. All right. So in this next, however many tens of minutes are left, plus next time, please.
Do you have thoughts about the fact that the C observer is at the same scale of the lightest massive particle that we know of?
Well,
as opposed to the heaviest. Okay, the strangest.
I'm not well. Yes, I mean I think about it all the time. There is another coincidence also, which it's roughly the seesaw between the Planck scale and the Wick scale. So like v squared over m Planck, it's also comparable. And well, let me say for the moment I have no thoughts, no reasonable thoughts. The only example that I know of that makes use of this coincidence, but not the neutrino one, but the seesaw one, is a paper by Nima, Savas, and Shamit, where they essentially build a multiverse where to get dark matter you need this seesaw. Okay, that's all I'm gonna say for on the record. Then we can talk off the record. Yeah. So, but to be honest, I don't know of any reasonable idea that really leverages this fact. Yeah, because I mean, in the end, as we discussed, it's always about symmetry, and if you want any symmetry, you have to extend everything. I mean, if you say it all comes from the neutrino sector, then you have to explain away the up to the 4 contribution, which is still there. Yeah, I'm sorry that I don't have a better answer, but I don't think anyone else does either. All right. So anyone else wants to ask something, or should I move on? Okay. So let me move now to the promised multiverse. So today or next time, I'm going to tell you also how a multiverse could be born. It's not so hard. I mean, okay, it seems like a pretty exotic concept to not live in a single universe, but have a multitude of universes. But in reality, you don't need that many ingredients. So if you have a theory, let's say, that lives in a few extra dimensions, when you compactify it to 4D, it has many vacua. And then these vacua could be long-lived cosmologically. You just need them to be either far away in field space or be split by a small amount compared to their absolute energy density. So tunneling from one vacuum to another, it's a semi-classical process which is governed by an exponential of the action. And so even, let's say, a mild hierarchy between the splitting between the vacuum and their absolute value in energy can give you an exponentially long lifetime. And so it's not so hard to have models where you have many vacua, and if you sit in one, you're not going to know about the others, even within the lifetime of the universe. If this is the case, you still want to explain why these vacua are realized as disconnected patches. So when we talk about multiverses, we're really saying that, okay, there is some space-time, and then an observer is in contact with some subset of it, and here the fundamental parameters have some values. And then another observer is in causal contact with another patch where these parameters have another value. Okay, so essentially you're imagining that, let's say, the theory has all these vacua. Here you're living in this one, and here you're living in this one. But how do you get to a configuration like this? Well, inflation kind of does it for you automatically. So let's say that you are in the situation we described before, where the universe is dominated by a positive cosmological constant with the scale factor growing exponentially. Then what happens is that you might start your life in one of these vacua with some values of the X mass and the cosmological constant and the other parameters. Then, okay, this volume is expanding exponentially. And even if the process of tunneling this other vacuum is exponentially long and unlikely, the total rate also depends on the volume that you have at your disposal, because to move from one vacuum to the next, you have to nucleate a small bubble, and you can do it anywhere in this volume. And even if the probability of nucleating a small bubble is tiny, you have to integrate it over the whole volume. So if you wait long enough, you will make a bubble. And so in this bigger bubble, you will be in your initial vacuum. And in this other smaller bubble, you will be somewhere else. So the parameters inside these bubbles and the X mass inside this bubble is different from the one outside. Well, at this point, I mean, you almost always tunnel respecting conservation of energy. In the Sitter space is a bit more complicated, but the most likely processes are those where you go to a lower energy vacuum. And so this bubble naturally would like to expand and eat up the whole universe. So the reason why we see one vacuum is because if there was a phase transition here, it would expand, the bubble would expand at the speed of light and eat all our universe. And that's the same reason why we see normal phase transition. So if you eat water, it will all boil. You will not you will have for a short time a phase where both gas and water coincide, which is the same short time in which you have both bubbles here, but eventually all the water will boil. And that's the same that wants to happen here, but inflation is kind of frustrating it. So this bubble is moving, this bubble wall is moving at the speed of light, but the space-time around it is expanding exponentially, much faster. And so you can easily have a bubble that is expanding inside another bubble that is expanding even faster. And this process can repeat itself many times. And if inflation lasts long enough, even if you have an exponentially large number of vacua, you might be able to see an order 1 fraction of them realized as all these nested bubbles that expand and expand. And again, at some point, they might expand so much that you are an observer living here, and your bubble is as big as the observable universe that we see today. There is another one somewhere else that is as big as the observable universe that we see today, and so on. One day, so when this exponential expansion ends, then the bubble walls moving at the speed of light will start entering the light cone of other universes, destroying them. And eventually, in a very long time, we will go back to having a single universe, all in the lowest energy vacuum. But this whole process of making the multiverse and then the multiverse going back to a single universe can last many, many lifetimes of the universe. And so we might imagine to be somewhere in the middle of this process. For now, let's just stop here, okay? Next time, I will tell you more precisely how you can get this vacua, and maybe I will also tell you how you can get this period of inflation. But for the moment, let's first see why this would be relevant for us. So imagine that, that this is actually the case, then, and that, I don't know, there is some theory where both the Higgs mass and the cosmological constant are calculable. So let's say that you believe that the description of reality at high energy is string theory with supersymmetry at the gut scale. Okay? Yes.
And isn't it possible that when these bubbles are expanding, that they touch each other, if by chance they are close to each other?
Sure. Yes.
Yeah.
Then, well, it will happen. So if you are outside, you will see energy released in the form of gravitational waves and other particles that are coupled, because these bubble walls, they are really, let's say, a profile of this field. Okay, let me say you have a toy model where you just have two vacua and a scalar field. This bubble wall is really just a solution of the scalar field that it's interpolating between the two vacua. So the bubble wall is just a region of space where the field has some value and some energy density. Okay, so when they collide, this energy density, so it depends. I mean, it might be this energy density annihilates into other particles. So whatever is coupled to this scalar can come out. Gravitational waves can come out. And then the two bubbles will merge, and whichever is the lowest energy vacuum will take over. That's very, very roughly the picture.
So that means that particles in the universe that are living in the highest level vacuum will start changing, like the parameters of this vacuum will start changing from one moment to another when we choose the smallest vacuum, the lower vacuum.
What do you mean from one moment to another? It's still a continuous process. I mean, it's the same way in which, I mean, let's say the bubble, when the bubble expands, the vacuum inside is taking over regions of, so let's say you are in the plus vacuum here and the minus vacuum here. As the bubble expands, regions that were before in the minus vacuum now are in the plus vacuum. And it's not very different when the bubbles collide. It's just that it's preceded by this more violent event where the two walls release energy.
Yeah, I had in mind, I had just in mind that if you were having, there was a particle that was living, and it just happened that it was created in the space where the two bubbles touch.
Like this.
Yes, and then if the particle has if its mass depends on the parameters of one of the bubbles,
Yes.
and it's not and it's the parameters of the bubble that is at the higher level. Then when there will be this shift, and we will switch to the lower vacuum. What will happen with this particle?
Yeah, so let's say this particle first crosses here and sees its mass change. I mean, since energy is conserved, it will get a boost in either the direction of the wall or the opposite direction. And same when it crosses the other one. So, or it might even bounce off. I mean, it might not be able, might not have enough energy to cross and get this mass change. So essentially, if you use conservation of energy, you will roughly get the right kinematics for what's happening. So this particle is going to have a mass outside, a mass inside, and some kinetic energy. And then that will tell you what happens very roughly. Okay, and then these calculations are actually pretty complicated because it also depends on whether there's many more particles in the plasma outside or inside. But this is the zeroth order intuition.
Sorry, may I ask? I don't understand why the larger bubbles expand faster than the smaller ones.
Yes, so this is kind of subtle point. The wall of a bubble, as seen from an outside observer, always goes at the speed of light. But the space-time inside the bubble can expand faster. So if you're an observer inside, say, the mother bubble, if you're close enough, you might see that this smaller bubble is expanding, but you're also seeing that you're moving away from it faster than the wall is expanding. If you're an observer inside the smaller bubble, you see only the space-time around you expanding exponentially, like we do now in the universe, and that's it. Yeah.
But you see an H lambda, the mother bubble has an H lambda which is larger, something like that.
The mother bubble has an H lambda that is larger. Yes, because typically yes, because the transitions that are preferred are those going to lower energy density. So H lambda is determined by the CC in your vacuum, and typically you go from high to low. So usually, yes, the bubble outside is going to have a bigger lambda. Actually, the most counterintuitive case is imagine that the bubble inside has a negative CC. Okay. Then from the inside, you see the universe crunching. So the space-time around you is contracting, but the outside observer sees the bubble front going towards him at the speed of light, because this is still the preferred vacuum, which is more, I mean, at a lower energy compared to the one outside. Okay. Let me stress that this is all a very rough intuition. So there are subtleties. For example, this space with negative CC has some finite radius of curvature. So it might happen that, and these bubbles have some energetics. So they have some energy on the surface, and this energy that they have on the surface should be smaller than the energy difference between outside and inside. Okay, so they're typically nucleated at some critical size, which is energetically favored. Okay, so you cannot make a bubble that is smaller than a certain size, because the energy in the wall goes like R squared. The energy difference between inside and outside goes like minus R cubed. So the bubble has always to be big enough to exist and be energetically favored. But the space inside the bubble also has a typical size. So let's say that you can only make a bubble which is bigger than the typical size of the space inside, then you're not going to make it. And so actually there is a clever idea for the CC that doesn't work, but I'm going to tell you about next time, which makes use of this fact. That going from lambda positive to lambda negative, you might be stuck because of this reason. You might not be able to make the bubble. Yeah. So, all right. Yeah, I went maybe too far on this picture. But let me tell you what this can do for you. Okay, so let me imagine that this construction is actually realized in nature, and that you have many of these universes, so many that in some of them, when you compute the cosmological constant, you have all these contributions that we were saying before. And somehow, just because from vacuum to vacuum all these parameters are changing, you find one where accidentally this is tiny. So this is the one that we observe, which is 120 orders of magnitude smaller than each one of the contributions. Again, these numbers might make you feel bad, but, well, we do expect in string theory to have enough vacua to have at least one where this accident happens. And to populate this vacua, so to create enough universes that this accident can happen, you need not that many folds of inflations. So to explain CMB, you need 60. To do this, you need something between a few hundred and 1,000. So you don't necessarily, so the typical picture of the multiverse that we will see next time is based on eternal inflation, where this exponential expansion of the universe continues forever, at least in some regions. But in reality, if you just strictly ask, how long does inflation need to last for me to populate 10 to the 120 vacua? The answer is not that much, okay? Okay, 1,000 defaults is still a very long time. By default, I mean, so it takes an Hubble time to expand by a factor of E. So when I say 1,000 defaults, I mean 1,000 Hubble times. So you need something of this order to populate this many vacua with some assumptions. So this number is very, very UV dependent. So I will say I'm secretly writing down some UV toy model where, say, the typical energy density in the vacuum is of order m Planck to the 4th, and the typical split in between the vacua is something like I don't know, say 0.1 or something between 0.1 and 10 to the minus 3. And then this precise number depends a lot on the details of the potential. So on really how the shape looks like. And, but for reasonable potential, say for reasonable splittings and let's say a Mexican arc really like this, with order 140 couplings, you roughly get order 1,000. Okay, that's a very rough toy model, but that's where my intuition is coming from. All right, so having made you feel a little bit better about populating 10 to the 120 vacua, what can you do with it once you have it? And I'm gonna do this fast, and then we stop. Well, you still have to explain why we're in such an unlikely universe. Because in the vast majority of these 10 to the 120 or more universes, the CC is going to be its dimensional analysis estimate. So the parameters are going to be order 1, and they do not conspire to cancel exactly to give us the observed value. So why are we in this lonely, unlikely universe? One possible argument given by Weinberg is that only these weird universes where the cosmological constant is much, much smaller than m Planck can accommodate observers. So in more detail, let me again go to this picture. So now to this picture of the universe, which is approximately homogeneous and isotropic, with some fluctuations in energy density. So not all the points in the universe have exactly the same energy density. Some have a little bit more, some have a little bit less. We even have a very nice way of getting these under and over densities in the universe from inflation. So what do I call a galaxy in this universe? A galaxy for me is going to be a place where there is a big energy fluctuation. So if you look at our universe, roughly, well, galaxies are a big overdensity of matter and energy compared to the rest of the universe, which is almost empty. So let me call very roughly a galaxy an order 1 energy density fluctuation in the universe. Then what do we need for galaxies to exist? So for galaxies to exist, we need the cosmological constant to be small enough that they have formed. Okay? Imagine a universe like the one we were talking about before. So you have some relativistic particle and their energy density is going down like a to the -4. You have some non-relativistic particles which are going down more slowly. And then you have your constant. Okay, one can show that these small fluctuations in all this time where the radiation is the dominant component roughly are constant, okay? They grow logarithmically with the scale factor, but it's a small effect. However, when non-relativistic particles start to dominate, which eventually will always happen, because they are diluted by the expansion of the universe more slowly than the relativistic particles, then whatever initial fluctuations you have are going to start growing linearly with the expansion of the universe. This is just the statement that gravity is an attractive force, nothing more and nothing less. And so we have measured what these objects are at the time when matter and radiation cross. This is what's called matter-radiation equality. And it's roughly the time of the CMB. That's why we know this number precisely. And so what we need to ask, essentially, is that these objects that at matter-radiation equality were roughly 10 to the -5, have the time to grow to order 1 before the cosmological constant dominates. If this is the case, then you have galaxies. If not, then the cosmological constant will do what we said before. Either it will expand the universe very fast, diluting exponentially these fluctuations, or it will crunch it, making it impossible for observers to exist if it crunches to, I mean, at least observers like us to exist, if it crunches to a small enough radius. And so what we're going to ask is that the energy density in the cosmological constant be smaller than the energy density at matter-radiation equality, amplified by the time it takes for these fluctuations to be order 1. Okay, since the matter-radiation equality, so the matter energy density goes down like the scale factor cube, and these fluctuations grow like the scale factor cube, this factor here is telling you how much the energy density in matter has decreased from the time it started dominating to the time when galaxies have formed. And interestingly, if you put in numbers, we measure this, which is EV to the 4. We measure these that I told you are 10 to the -5. Here you get more or less the observed value of the cosmological constant. If you run the argument a bit more precisely, you get something that is about a factor of 100 to 1,000 off. But it's quite remarkable that to have galaxies in our universe, you need the cosmological constant to be roughly what we see. Okay, and so this is the argument of Weinberg for why we exist in such an unlikely universe. Because in all the others, galaxies never formed, observers never formed. You might worry that this argument is a bit too detailed. So why galaxies? The answer is that you can weaken this argument a lot, but still the basics of it remain valid. So all you're asking here really is that you have enough energy within an horizon to create complex structures, right? So if your universe expands so fast that all that's in causal contact with itself is an atom, you will never have observers, obviously. Similarly, if it crunches to a size so small that it's smaller than an atom, presumably you will also not have observers. So this argument is just some detailed version of asking that within an horizon you have enough entropy to explain us, or at least a star.
On the contrast that are over and off.
Yes, so that's what I was about to say. So obviously this argument works exactly as is, only if you imagine that the other parameters are fixed. So if you start saying maybe this is also changing from universe to universe in a multiverse, maybe this is also changing from universe to universe, then okay, you will not get this striking number exactly on top of what you observed anymore. But since we're running out of time, I encourage you to try. This argument is much more robust than for the X.
That's another law, 10 to minus 5, I think 10 to minus 3, their power, because 6 orders minus off.
That's true.
It's not that good.
Well, it's true yes, but well, I mean, in the end, this really enters as 3/4. So okay, so this rho lambda here is what I was calling lambda in the Friedman equation, the Einstein equation, which is also lambda cc squared. Sorry, lambda cc over m Planck squared. And then here you're saying, then here you have something like, so what the cc is really m Planck times, so the energy scale, so the lambda cc to the 1/4, it's really m Planck to the 1/2 times matter radiation equality delta rho over rho cube all to the 1/4. So really, if you care about the energy scale, the dependence is pretty mild, and also you have this big factor of m Planck in front. So what I was saying is try to put the numbers. You will see it's not as bad as you think. I mean, I also did it because I was bothered by it. You will see that indeed, I mean, you can change the scale by a few orders of magnitude pretty easily, but you can never make the cosmological constant f top or even, yeah, I don't think even lambda QCD. I mean, maybe you can barely get lambda QCD. I forgot, but well, exercise for the viewers. All right, so I think this is a perfect place to stop. Thanks for bearing with me.
Question? Online, do you have questions? Okay, so thank you.